Hello, and welcome back to the third video in our video series that is revolving around demystifying AI for engineering educators. So just as a quick note, my name is still Peter Simpson. I'm a lecturer at University College London in the Mechanical Engineering department. Today we're actually going to be covering machine learning. So machine learning is something that is spoken about a lot with respect to AI, and we're going to define some of the key characteristics of it and also look at the implementation within engineering specifically. So we're going to talk about some key terminology, some key concepts, and then more about the application. Now, without further ado, let's get into it. So what is machine learning? Machine learning is mentioned a lot. I think it's bordering on becoming a buzzword at this point, but machine learning is realistically a function that learns patterns from data. That's how you can see it. It's trained to minimize certain metrics, and it kind of does form that brain as we've alluded to in other videos. So again, it takes all of that data in and starts to analyze it and spot those little patterns that we see across AI being utilized to actually make those predictions at the end of it. Now, the key here is that there are different types of learning. And as this slide mentions, not all learning is equal. We have 5 different types of learning that are kind of commonly utilized in today's kind of AI applications. The first is supervised learning. This is learning from labeled examples, so you have an input and a correct output. So we actually mentioned this when we were talking about annotation in our data pipelines. This is a very important step for supervised learning. And an engineering example of this would be predicting weld defects using labeled images. You label where that defect is happening, and then that allows the AI algorithm to predict that in future images. Next, we have unsupervised learning, which is basically the opposite. You're learning patterns, or your algorithm rather, is learning patterns from unlabeled data. So a really realistic example of this is clustering CAD geometries based on shape similarity. They are not labeled, it just simply sees what it can see, and if they're similar, it puts them into a group. Next, which is kind of a hybrid of the first two, is self-supervised. You use a small amount of labeled data plus large amounts of unlabeled data to then predict where that label might apply in the future. So if we're looking at this from an engineering context, we might be looking at models where potentially there are missing surfaces within our CAD. What we could do is feed it some correct and labeled inputs, and then it could start to extrapolate where those surfaces might be in the incorrect, not complete CAD. Our fourth option is in-context learning. So this is learning by predicting missing parts of the data, which works really well if we don't have that lovely, complete, good quality data set that we want. So some kind of non-engineering examples of this would be, what's the next word in this sequence? What's the next frame in this video? But if we're looking at an engineering application, a lot of text-to-CAD workflows that are currently being developed are utilizing this form of learning. It's allowing a model to purely utilize a written prompt to then get into a 3D model. Finally, we have reinforcement learning. Now, this can be really powerful if used correctly, and that's the ability to learn to make decisions by interacting with an environment, taking actions, and receiving feedback. Now, it's a little bit harder to imagine, but an easier way to kind of imagine this is looking at a robot arm. A robot arm is maybe assembling something. There are almost infinite amounts of paths it could take between point 1 and point 2, but there probably are more optimal paths. So the robot arm might try a few different paths, and then through trial and error or maybe some user input, work out which one is the most efficient, whether that's in time taken, maybe it's to do with some sensor readings of proximity to other things. It allows it to actually learn by reinforcing positive actions, positive movements. Now, bear with me for this one. We are just going to have to define some key terminology to enable you all to speak machine learning. As I mentioned, I think in the very first video, we're just trying to have this as almost like a little translation so that when people talk about these specific details, you can then come in and be like, oh, that's machine learning. Let's go. So first is gradient descent. This is an iterative optimization algorithm for finding the minima of a function. Next, we have epoch, which is one complete pass through the entire training data set. something that we mentioned in our second video to do with data. Generalization is a concept to do with the model's ability to handle new data that is different to our training data set, something that we really want to achieve. Overfitting we have mentioned before, but this is when a machine learning model learns our data too well, including potential errors and noise, so actually will perform poorly on new data. That's why we spoke so much about the split of data in our last video. To kind of counteract that, we also have underfitting, which is when our model is potentially too simple to capture the true patterns in the data, leading to a lack of pattern recognition again. Our final two are data leakage, which is hidden correlations within the data being picked up that we necessarily don't want to be picked up. And we also have our distribution shift. This is when the data's properties vary between training and actual data set, and this can cause our AI algorithm to kind of get a little bit lost, to be honest. Now, when you hear about machine learning, a lot of people will publish that they're doing deep learning. But what they're actually saying is that they're using deep learning, not narrow learning. And here are the differences. So with narrow learning, we're using simple models, linear regression, decision trees. If X, return Y kind of thing. It learns patterns very well for a specific task, but needs very structured data sets and can work well with less data. So uses for this might be something like quality control, where we're saying this is good enough, this isn't. If it has this kind of a defect, remove it. This is very simple, doesn't require that much data or input, just requires a simple if X then Y. Next we have deep learning, and this will actually be the topic of its own video, the next video in the series, because it's that complex. But this uses multi-layer neural networks and can enable you to actually spot complex patterns. This excels with less structured data, a data that we kind of explained was quite problematic in the last video, but does require a huge amount of data to be used correctly. And this is basically effectively the basis of most of the applications that we think of. Most of the foundation models are actually built on deep learning, so it is a very important thing to mention. Now, there are some severe limitations that we need to understand. The first one being data. Ultimately, we've already spoken about this in its own video, but without large high quality data, we are going to struggle to learn these kind of different methods and these different patterns. The next is accuracy. Machine learning cannot cope with that distribution shift. It is vulnerable to bias, noise, data leakage, all of those fitting issues that we've discussed. So actually this does not ensure accuracy, it actually opens up a whole new avenue for inaccuracy. Finally, I think a key one is actually our understanding of it. I think I referred to it in video 1 where we're talking about trying to make AI not like this little black box where everything goes on and stuff comes out the other end of it. And sometimes with these learning algorithms, that is just forced upon you because they're learning themselves. It's hard to find out exactly what went wrong, and many relationships are so small that we just can't really fathom them. And that makes it very hard to diagnose problems. So, how might we actually teach machine learning? Because that's ultimately what we're all kind of doing in our day-to-day lives. Well, I think the thing with machine learning is that it is very complex, but we can start very simple. Machine learning is iterating around finding patterns and taking those forward. So even starting with an example of, can you find the pattern in this series of numbers? You could then go one step further and start to remove numbers from the sequence, add numbers, and show how hard it is to find patterns when you're actually working with incomplete or maybe smaller data sets. That allows you to explain the basis of what machine learning is doing. The key here really, I think, for machine learning is start simple and build that complexity into your teaching. If you go straight in with deep learning and start, firing off machine learning algorithm names, it's ultimately going to end up with a lot of misconceptions, maybe misunderstandings, and maybe a bit of, let's say, overly estimated confidence in the machine learning algorithms themselves. So we need to start with the core basics. What are they doing? How are they doing it? Things like the different types of learning are a very key concept to teach in this style of teaching. I hope you've enjoyed the video, and hopefully I will see you in the next one.